Hello guys, and welcome to a new lecture about linear algebra. In this lecture, we are going to study the concept of orthogonality. We already investigated the operation of addition and scalar multiplication for vectors. In this lecture, we will study length and perpendicularity. These operations fall in the concept of geometry. By combining the geometry of vectors with matrices in linear transformation, we obtain powerful techniques for solving a wide variety of problems. For example, we can use them for least square approximation, like we can do linear regression, we can do many other techniques like for computer graphics, for statistical analysis, and many others. To do so, we are going to solve the issue of construction of a basis of perpendicular eigenvectors for a given matrix of linear transformation. We will see how to convert any basis for a subspace of like Rn into one in which all of the vectors are perpendicular to each other. Then we will try to specify conditions that guarantee there is a basis like for Rn, which consists of perpendicular eigenvectors of a matrix or a linear transformation. So the topics today are norm, distance, orthogonality, dot product, orthogonal complement, orthogonal projection, and least square approximation. The first prerequisite that we need to learn is the concept of norm and later distance. Perhaps the most basic concept in geometry is length. In our middle school math, we learned Pythagorean theorem. Based on the Pythagorean theorem, in a right angle triangular, the square of the length of hypotenuse, as you can see here, like this vector u, is equal to the sum of the square of the lengths of the other side, like this one and this one. So we learn that u2 is equal to u1 square plus u2 square. This is known as Pythagorean theorem. Pythagorean theorem. Mathematically, we can derive this one. U is, because this is a square, this one can be rewritten as u is the square root of u1 square plus u2 square, as you can see here. We can apply the same theory to any vector v in Rn. And we can come to the concept of norm. We denote by this one v, where v is equal to the v1 square plus v2 square plus 2, any of them. So this is called as length or norm. A vector whose norm is 1 is called as unit vector. So if v is equal to 1, then this v is called as unit vector. Also, this is we call as magnitude as well, norm or magnitude or length. Using the definition of vector norm, we can talk more about the concept of distance between two vectors. We can state the distance between two vectors like u and v is shown by the norm of v minus u, the norm of v minus u. So if we have, for example, vector v is equal to 1, 2, 3, and vector u is equal to 2, minus 3, and 0, then we can do like this and get the u minus v. Then the norm will be 1 square plus 2 square plus 3 square of v is root square of 14. For the case of u, we go for this one, and u minus v, we can come to this value. This is the distance between the two. So if this is v vector and this is the u vector, the distance is something like this, right? This is u minus v, and this is the norm. Later, we will use this concept for projection, and in linear regression, also we will try to use these concepts. In order to learn the concept of orthogonality, we should know dot product. Dot product is the multiplication of corresponding components of two vectors. Orthogonal vectors represented by u and v poses a unique mathematical property. It means their dot product is always equal to 0. So if dot product of two vectors is 0, then we can say that they are orthogonal. They are orthogonal to each other. This property implies that the vectors are perpendicular in geometry. Perpendicular. The same concept, orthogonal and perpendicular, is the same. Additionally, it is important to note that the 0 vector is orthogonal to any, because 0 vector dot any other vector is equal to 0, right? That's why 0 vector is orthogonal to any other vector. These characteristics rise from the fact that the dot product of any is equal to 0. Dot product of 0 to any is equal to 0. These things, we need them later. So in here, this is one example. We have three vectors like u, v, and w, and we want to check which pairs of these vectors are orthogonal. To do so, simply we check their product one by one, or a pair of product, if dot product is equal to 0, it means they are orthogonal. Right? We check. First, we go for u product v. 2 by 1 minus 1 by 4, 3 by minus 2 is equal to. These u and v are not orthogonal to each other. Then we go for u and w again. 2 and minus 8, minus 1 and 3, 3 and 2 again. Not orthogonal to each. Then we go for v and w. 1 minus 8, 4, 3, minus 2, 2, which is 0. So we conclude that v and w are orthogonal. So these are some characteristics of the product. If we have two vectors like u and v, and we have a matrix as a and c as a constant, geometrically the dot product, the product of magnitude of the two vectors. So based on these uv vectors, a matrix and c, we can go for some properties. The first one is u dot u is equal to norm u square. This is called as magnitude and dot product connection. This connects the dot product with the squared magnitude of vector u. The second one is 0 dot product implies 0 vector. This is 0 vector, right? Means u dot u is equal to 0 if and only if u is equal to 0. It means one side should be 0. The dot product is 0 only when a vector is the 0 vector. Then we have u dot v is equal to v dot u. This is, we can say that dot product is commutative. Dot product is commutative. Then we can go for distributive property. In the distributive property, we can say u dot v plus w is the same as u dot v and u dot w. We can say the dot product distributes our vector addition. In scalar multiplication, the same thing is here. In the case of scalar multiplication, the dot product interacts with scalar multiplication. So we can say c u dot v, which is equal to u dot c. Then we go for norm of scaled vector. The norm of a scaled vector is the absolute value of the scalar multiplied by the norm of the original vector that we have here. Then we can go for matrix vector product and transpose. A u dot v is equal to a u transpose b, which is equal to u transpose a transpose b, which is equal to u dot a transpose v. So these are, and here is the example, like 2u plus 3v is equal to norm of 4u squared plus 12u dot v. That is, these are properties of dot product. In many cases, we need to approximate a given vector by a vector in particular subspace. In this situation, we need to find the best possible approximation by choosing a vector in the subspace that is the closest to our main vector. To solve this issue, we need to study what is orthogonal complement, what is orthogonal projection, how to do orthogonal projection. So the orthogonal complement of a non-empty vector is denoted by a spread. Read this one as spread. This is called as orthogonal complement. So orthogonal complement or spread is the set of vectors that are orthogonal to every vector in S. So we say S spread is V, where V dot U is 0. This is the meaning of orthogonal, right? So a set of vectors that are orthogonal to every vector in S, we show in this way. So S of the subspace of Rn, then we can go for this one, right? And you can see here, this is what we can see, it's orthogonal, this W prep, orthogonal to W. So we learned that S perp is the set of vectors that are orthogonal. This means orthogonal to every other vector in S. Suppose we have W as the xy plane as a in R3, for example, or R2. Then the vector like V, like for example V1, V2, V3, lies in W perp. If and only if V in V and W V dot W is equal to 0, right? Then we say W perp is the subset of V, where V is the set of vectors, where V is the set of vectors. So in this case, we can say W perp is 0, 0, V3, where V3 is in R. Let's see one example to better understand the concept of orthogonal complement. In this example, we want to find a basis for the orthogonal complement of W, which is span. In this case, we must find some vectors those are orthogonal to this U1 and U2. Here is U1, the vector of U1, and here is vector of U2. To find a basis for the orthogonal complement, we assume another helpful vector like V, as you can see, V1, V2, V3. Then we write this V as a system of linear equation based on this one here. 1v1 plus 1v2 minus 1v3 plus 4v4 is equal to 0. Then based on this one, we will go for the next equation, v1 minus v2 plus v3 plus 2v4 equal to 0. If we try to solve the system of linear equation, you already know how to solve this one. I show many examples using, for example, REF and many other ways that we can come up with this solution. x1 is equal to minus 3x4. Then x2 is equal to x, or you can say v. You can say v2 is equal to v3 minus v4, and v3 is equal to v3, and v4 is equal to v4. So we write the same thing here: minus 3v4, v3 minus v4, v3, and v4. Then we can come to this general form that v3 in here. For v3 we have 0, for v3 here we have 1, for here we have 1, and here we have 0. Then before we have minus 3 here, minus 1 here, 0 here, and 1 here. So these are the two vectors that are complement to this one. We can say this is the basis as basis of W perp. Let's see some more properties of orthogonal complement. The first one is S perp as a subspace. Always forms a subspace when S is a subspace or collection of vectors closed under vector addition and scalar multiplication. For any non-empty vector set like S, the orthogonal set of this S perp or span, this one, is equal to the perpendicular of S. If we have W is a subspace with basis of B, the orthogonal or B perp is equal to the W perp. And the intersection of S and its perpendicular set is always equal to 0 vector. Now we are ready to study the properties related to matrix and subspace orthogonality. For any matrix like A, if A is a matrix, the orthogonal complement of the row space of A is equal to the null space of matrix A. If V is in the perp of row A for all W in the space of row A, the dot product of W and V is equal to 0. This is equivalent to the AV is equal to 0. Then for the column space orthogonality, the orthogonal complement of the column space of A, which we show in this case, is equal to the null space of transpose A or null AT. The orthogonal space of the column space of A is equal to the orthogonal space of the transpose of row A, which is also equal to the null space of D. Then for dimension relationship in subspace, for any subspace W, which is in Rn, the dimension of W plus the dimension of the perpendicular space of W is equal to n. The dimension of W is equal to the rank of W, and the dimension of perpendicular space of W is null T. For any subspace W which is in Rn, the sum of dimension W and its perp is equal to the dimension of the ambient space N. So mathematically we write time W plus time W perp is equal to N. And in the dimension W, the dimension of W is represented by the basis of W1, W2 to Wk, where K is the dimension of W. And in case of dimension of W perp is represented by the basis of Z1, Z2 up to Zn minus K, where N minus K is the dimension of W perp. The union of bases for W and W perp form a basis of the entire subspace of Rn. the dimension of W and dimension of perp is always equal to n, as we have here. And for every vector u in Rn, it can be uniquely decomposed into a sum of a vector w and z. A vector in w and a vector in w perp, which show it as z. So this w in w and z in perp, which is called as uniquely decomposed. So mathematically, we can write u is equal to w plus z, and this is the decomposition is unique. Here also we have, for example, this is w, and this is z, this is e, right? We can write u as the projection or complement that we can have. The next topic that we are going to investigate is orthogonal projection. Orthogonal projection. Suppose we have w as a subspace of Rn, then the orthogonal projection of u, this is u vector, and suppose this is w, right? Then the orthogonal projection of u on w is the unique vector in w, as you can see here, such that u minus w is orthogonal of w, or perpendicular of w. Do you know what is the concept? Suppose you have a light, right? A torch, for example, here. If the light come here, what is the image or shadow, right? You can say this is shadow. Shadow of this vector on this subspace. This is called as orthogonal projection. We want to find out the shadow of u on this w plane. This is w plane, right? And this is what you can say. And this is orthogonal. You can see this is 90 degrees. And this is called as the distance between these two. So this is the distance u, or you can say here z is equal to u minus w, the distance. And here u underscore w is the orthogonal projection of u on w. Sometimes they say project, right? Project of, for example, u on w is equal to small w. So u underscore w, u or project u, is the orthogonal projection on u on w subspace. And the line segment connecting the endpoint is the space here, length, right? So you can say u is equal to w plus z, or z is equal to u minus w, right? This is z. W is in the subspace and z is in w perp. This is called that orthogonal projection. Among all vectors in subspace w, the vector closest to u is the orthogonal projection. So here, the relationship between vector u, v, and v prime in subspace w we can see. So for any vector like w, w prime, and w minus w prime in subspace w, the dot product of u minus w and w minus w prime is always 0, right? You can see here, this is u, right? And this is w, this is w prime. So this is the norm of u minus w prime. This is the norm of u minus w prime. And you can see. So we can write mathematically that u minus w dot product of w minus w prime is always 0. The norm squared of the difference between u and w prime is equal to the sum of the norm square of u minus w and w minus w prime. We can mathematically write in this way. Expressing u minus w plus w minus w prime as the sum of two vectors, u minus w and w minus w prime. So mathematically we can write in this way. The norm squared of u minus w prime is strictly greater than the norm squared of u minus w, and mathematically we can write in this form. These statements reflect the properties of orthogonal projection, and these emphasize the orthogonality and the composition of vectors in subspace w. The distance from a vector u to subspace w is the distance between u and the orthogonal projection, as we have seen here. Any orthogonal set of non-zero vectors is linearly independent. This means that if we have a set of vectors and each vector in the set is orthogonal to every other vector, then the set is granted to be linearly independent. This is the conclusion. The proof for this property is based on the fact that if vectors are orthogonal, their dot product is equal to 0. You already know. And this condition ensures that no non-trivial linear combination of these vectors can sum up to the 0 vector. Therefore, each vector in the set contributes uniquely to the linear combination, establishing linear independence. Additionally, any orthogonal set has an associated orthogonal projection matrix, which we show it by PW. This matrix projects vectors onto the subspace spanned by the orthogonal. This one that we can, and this is our subspace, this is u vector, w vector, and these are orthogonal to each one. This is the distance between them, this is the v. Then we can come up with the matrices. This matrix is a kind of standard matrix for orthogonal projection that we can write it in this way. PW is equal to A transpose A inverse A transpose. We can write it in this form where this A is the matrix whose columns form the orthogonal set. This formula ensures that the projection matrix is orthogonal and it projects a vector onto the subspace spanned by the orthogonal set. The next topic that we want to study is how to do orthogonal projection, how to find it. So we have a line like L, this is a line, and we have a vector like V, right? We want to, for example, we have a torch here, right? And lights come here. We want to see what is the shadow of this vector V on line L, Or we want to find the projection of a vector. So this is called as projection of vector V on line L. V can be any vector, U can be any non-zero vector on here. So this is vector U, and W is orthogonal projection of V onto L, and Z is equal to V minus W. This is the distance, right? This Z is the distance or distance between V and the projection. In this case, V minus W multiply U is equal to V minus CU multiply U. CU means any scalar or any scaled vector. This is called as a scaled vector that U is equal to V dot U minus CU dot U, which is equal to V dot U minus C, the norm of square of U. And to find C, we want to know what is the scaled vector. We will go for this formula. And once we found C, then we will form this one to find out the projection of V on this line. The distance is here. This is the distance from here to here, which is equal to norm of Z, or distance is V minus W, the norm of the which is equal to V minus V dot U, U square. This is how we can find projection of one vector on a line. So this example helps us to understand orthogonal projection. Suppose we have vector V, and V is 4 and 1. So 1, 2, 3, 4. This is 4 and this is 1. So V is 4 and 1. Then we have U here as 2 and 1. And we have a line here, this dash line, which is equal y 1 by 2x. Now we're going to find W. W is the projection of vector V on line L. Projection of vector V on line L that we have here. To find it, V multiply U divided by square of norm U multiply U. So 1 by 1. V vector is here 4 and 1, U vector is here 2 and 1, divided by norm of U, right? So norm of U is 2 square plus 1 square is equal to root square of 5, and this one square, so it will be equal to 5. So it is 5. Then multiply U is 2 and 1. So this one, so we have 4 1, we have 4 1 multiply 2 1. So it will be 4 multiply 2 plus 1 multiply 1, which is equal to 9, right? So we have 9 here, we have 5 here, and 2 1 here. So 9 by 5, and 9 divided by 5 multiply 2 1. So it means 9 divided by 5 into 2. So it will be 18 by 5, which is equal to 3.6. Then this one, 9 by 5, and 9 divided by 5 is 1.8. So we find W as this one. So this vector is what? It is here, 3.6, and 1.8 here. 1.8. So this is the projection of V on line L. We want to find the distance between V and W, right? Distance between V and W. So V and W, 4 and 1 as V, and W we find here. So 4 minus 3.6 is 0.4. 1 minus 1.8 is minus 0.8. Then we're going to find the norm. The norm of V minus W is root square of 0.4 square plus minus 0.8 square, which is equal to 0.8, right? Root square of 0.8. So we can write 0.8 as root square of 4 divided by 5, which is equal to 2 divided by root square of 5, and that is 0.89. This is the distance between W and V. So what we did here, we had a vector like V, we found the projection on this line, then we find the distance as 0.89. Whatever we discussed so far has a one good application, which is a statistical procedure. Also in machine learning and data science, we use it a lot, linear regression. So we are ready to study one interesting topic known as linear regression. In many research problems, we are interested in finding simple mathematical relationship between variables. You can say between two variables, between many variables. For example, we want to find the price of a car based on its age, or the price of a car based on its age, model, and the options that they have. In this case, the price, so we have two kinds of variables in here. One is called as independent, and one is called as dependent. In the case of price prediction or price estimation, so linear regression is used for continuous prediction, for example, or estimation. In the case of car price estimation, the dependent variable is price, because we are going to estimate price based on what? It can be based on age of a car, for example. It can be based on model. It can be based on user history. It can be based on accident history. It can be based on several options that it may have. So what we do here, we have a set of data, for example, price of cars, 1,000 price of cars. We have the data, we know what is the price and what are the options. We build a model based on the data that we have, and later we use this data for unseen data, for new car, right? We have deterministic relationship. In deterministic relationship, data about one variable completely determines the value of another variable. On the other hand, we may have probabilistic or stochastic relationship. We can use orthogonal projection to identify relationship between variables. In figure here, you can see these are the data points. For example, maybe car price in something, right? We have known data. It means we can say we can get from our data set, right? Set of data that we have. And this blue line is estimation. This blue line is, for example, you can say this, they call it as regression line. Regression line, also called the least square line, right? So we want to find out some line which is projected. You can see this one is projected here, this one is projected here, this one is projected here, and then we try to find out this line where this line can be representative of our data, and later based on this line we can predict. For example, one car can be this price. We can say, okay, the price for this one is something like here, right? This is called as linear regression. So we listed the error. Error is the distance between actual data and predicted one or estimated, or you can say blue line, right? The distance, right? This is the distance. So you can see z, you remember z? So we can say y1 minus a0 plus a1x. This is the line, right? This is what we have here. Our main objective, is here. We want to find out a0 and a1. These are called as parameters, in such a way that this error is minimized. We want to minimize it. It means we want to adjust the line in such a way that distance between data points and line is minimized. And E will be defined like this: y1 minus predicted one, actual minus predicted, actual minus predicted. Suppose we have three vectors like v1, v2, and y, and we have c like as a v1 and v2. In this case, we can write the error equation as E is equal to the norm square of y minus what we have predicted, and here is the error as we have in the previous example. We want to minimize E. We need only choose the vector in W that is nearest to y, but from the closest vector property, this vector and the orthogonal project on y that we can see here, that based on the previous slide that we discussed. So for any reasonable set of data, the x that we have are not equal, and hence vector v1 and v2 are not multiplied of one another. Thus, the vector v1 and v2 are linearly independent. So we can say v1 and v2 are linearly independent. And so the base of v1 is equal to v2 is the basis for the w. Since the column of C form a basis for w, we can rewrite C a0, a1, these are the parameters that we are going to find, is equal to C transpose C inverse, C transpose Y. And multiply on the left side by CT, we can get CT. If we multiply CT, C transpose from both sides, then we can get this way, which is equal to C transpose Y. The matrix equation CX is equal to CTY correspond to a system of linear equation that is called as normal equations. So the line of best fit occurs when A0 and A1 are the solution of normal equation. Because C transpose C is invertible, we see that the least square line of the equation is equal to y A0 plus. This is called as regression line. Regression line. So we can say that A0 and A1 is equal to CTC inverse CT y. We want to try, this is called also intercept, and this A1 is called that slope, right? So intercept, when you want to draw a line, for example, this is intercept is the point that this line crosses the y-axis, and a slope is a slope, right? So this is one slope, this is another slope, this is another slope, right? This is the rate of changes in the line. So example is here. We have some data like x and y, as you can see here. This can be any data, and x is independent. X is our independent variable, and yi is dependent variable. It means we want to estimate y based on x. So we just suppose that c, we already know that c is equal to v1 and v2. So that one, we consider one as v1, and we can form our c as this one, and y, so this y comes from this data, right? Then we calculate c transpose c. So c transpose c, it means 1, 2, 3, 4, 5, and this data multiply c, which will give you this one. Then we multiply this one by this, cty, we give you 10 and this one. Then we can find out a0 and a1. a0 and a1 is ctc. It means we multiply ct this one, and we find inverse. The inverse will come here, multiply c transpose, multiply y will give us this one. So what is the use of this one? We can form our line, right? This is, that one is the blue line. That is the estimation that we want to try. So it means a0 is this one, a1 is. What is the use of this line? For example, we want to predict or estimate y for this value. As you can see, 2.65 is not here. This is new data, right? We want to predict based on this data. If for 2.6 it is 2, for 2.72 is this one, what is the value of y if x is equal to 2.65? So we put it here, right? Not 0.056 plus not 0.74, multiply this one, which gives you. So in the case of 265, the value of y will be 2.03. In the previous slides, we studied linear regression. Linear, it means what it was a line, where we tried to find out a line as the representative of data with minimum possible distance, or we try to minimize the error. Linear equations produce straight lines on a graph that we already tried. However, quadratic equation result is parabolas. This is in mathematics, we call it as, right, or something like this, right, or this one, right, or this one, right. These are called as parabolas. Parabolas. Then in here we try to find out an equation with one variable with power of. In linear we have power of 1, but in here it's non-linear. We may have power of 2. You can see here. So we have an additional 4. In the previous slide we have up to here, right, it was linear, but when power of 2 is here, then we call it as, so linear is good, and we call it as quadratic, right? If you want to do linear, we cannot minimize the error in any case, right? It goes, better goes to for parabolas. Like what we did in the case of linear, here we also try to find out the distance of each data point to our here. So this is the error, the same as what we did in linear, y minus, this is actual values, and these are predicted values. Then we try to minimize the error. Here we can see that mathematical presentation of this quadratic feat, like what we did in case of linear regression. We have v1, v2, v3, and y. Then we will try to find out the error, and based on that one, we try to minimize e, and finally we can get a0, a1, and a2 as c transpose c inverse cty, in the same case that we did for linear regression. Suppose a ball is thrown upward from a building of 100-meter feet. This is the height of building in feet, and we throw the ball at a velocity of 30 feet per second. The velocity is equal to, so velocity is equal to 30 feet per second. Based on known equation in physics, we can say that the height of the ball after t second is equal to s0 plus v0 t minus 1 by 2 g, and this g is the acceleration of gravity. The height of the ball is observed at the time given in this table that we have. In time 0 it was at 100, in time 1 it was here, in time 2 it was 92, in time 3 48, in time 3 7, and finally in this time it touched the ground. For the data provided, we form the C, as you can see here. This is the C, and this is our y, right? So the quadratic polynomial is y is equal to a0, a1x plus a2x squared. That is of best fit that satisfy this equation. So this is in here, this line is the quadratic polynomial of best fit for the data that we have in our table. So we finally, after all this calculation to find out the parameters a0, a1, and a2 based on this equation, we will come up with this one, and we make this problem that we have, right? And if we consider 1 by 2g, we consider 1 by 2g as the minus 16.11, we obtain the value of minus 32.22 feet per second as the estimation of g. The last topic is multivariable least square approximation. This is a kind of trying to find best fitting line relationship between multiple, in this case we have multiple independent variable, and we have one dependent variable. So in linear regression, we tried, it was 2D, right? So we tried price based on age. But if you want to do price based on age, model, options, then we have to go for multivariable. This multivariable least square approximation extends the concept of least squares, and this least square minimizes the sum of square difference between observed and predicted value. So as you can see here, we have different variables. You can see these are different independent variables. So this is how we can try to find the best. So this ya is our dependent variable. We want to estimate this one best. And as you can see here, this is a plane, not a line, right? This is a plane. Then we try to do projection and we find out how it works. Okay, at the end. So in this lecture, if you want to summarize what we have studied, we studied norm that measure the size or length of a vector in a vector space. Then we learned distance between vectors, which was the magnitude of difference between 2 points in a space, and we use norms to find out that one. Then we studied orthogonality. Orthogonality vectors, we say that if their dot product is 0, it means they are right angle between each other. Then to find that one, we studied dot product of two vectors, which was sum of the products of their corresponding components, and the output was a scalar. Then we studied orthogonal complement of a subspace, which was a set of all vectors orthogonal to every vector in the subspace. Then we studied orthogonal projection. It's a kind of transformation that projects a vector onto a subspace, and we try to minimize the distance between the original vector and its projection. And finally, we studied least square approximation, which was a method for finding the best fitting linear relationship between variables when there is no exact solution. And we try to minimize the sum of square difference between observed and predicted value. We also tried for nonlinear and for multiple. Please study and feel free to ask me if you have any questions. Thank you.